Now, I'm going to have to do some cancelling, right? But you've got to be cautious. For instance, this part here, do you remember when we first introduced inverse trig, okay? I actually made a big deal to say sine, or sine inverse, say, of sine alpha, right? This is equal to alpha, but only sometimes. Do you remember why? Only sometimes. They don't simply, despite being inverse functions, they don't just magically cancel each other out. For what values does it work? Now, this is inverse trig, right? So it was a while back. You can draw it out if you want. What you're going to get, if you were to graph sine inverse of sine something, you'll get this graph. Does it have endpoints? Yes, it does. From 1 to minus 1. It's a straight line. So it does look like you get the same function when you get it back. It's just like y equals x, okay? But it only works within here because, for instance, let's put some angle in there, okay? Put in, say, pi on, I don't know, pi on 2, okay? Sine of pi on 2 is, 1. So take sine inverse, and that's okay, right? But if you put some really huge angle in there, like 15 pi or something like that. Actually, what is sine of 15 pi? You don't tell me the answer. 15 pi. Come on, sine's a simple function. It just goes up and down and up and down and up and down. Every multiple of pi, sine should be equal to 0, right? So you've got sine of 15 pi in here, right? Which is 0, okay? So when you take the sine inverse of that, you've got sine inverse of 0, which doesn't take you back to 15 pi, does it? What does it take you back to? Just takes you back to 0, right? Because that's the closest value to the origin that gives you that result. Okay? So this is not always true. It's only true for, let's see, let's do the next line, shall we? Minus 2, x on 2. This statement is only true when you have this domain. Okay? This domain, between minus 1 to 1, that's the domain of sine inverse. Okay? In other words, minus 2 to 2. Okay? Now, I don't know about you, we're not finished yet by the way, but that kind of bothers me. The fact that you're getting an answer, but your answer is only the legit answer for some values of x. Like, in other places, our answer's wrong. But that turns out to be not a problem here. Can anyone tell me why? We missed something very, very early on. You want to see it? Aha! That domain restriction, this one here, right? It lines up, not very coincidentally, with the domain restriction you get from here. Okay? So in fact, what we really should have done is taken note of it there. Okay? So get a big red, green, purple, whatever color you use to highlight things. Okay? And take note. Write down. Okay? Domain restriction. You have a choice. You can mention it here. Okay, you can mention it right at the front, or you can mention it later on when you really need it, which is when you're simplifying this sine inverse sine thing. Okay? When do you think is the best place to do it, given that you have a choice? When would you mention it? First or later? Earlier or later? I think earlier. Why? Why is that a good idea? It doesn't matter. So, if you're like me, you will get through all these lines of working, and then by this time, it's a bit like when they make you do the warm-up for PE, and you're like, you got to do 1.6, you do a warm-up, you do your warm-up, and then you're like too exhausted to actually run the 1.6, okay? So by this time, your brain will be so fried, I will bet most of you will forget this, okay? So it's better to mention it right at the beginning. When you see a square root, or when you see a fraction, you should notice the domain restriction, okay? Secondly, with any other question where we've got domain restrictions, we always mention them at the beginning, right? So I think it's probably a good practice to get into. So, we're fine, good. That sine of sine inverse of x on 2 just turns into x on 2. What about this guy? Cos of sine inverse of that. Yeah. I'm going to have to draw it, okay? But the question is, draw what? Now, remember, sine inverse of something, right? Just refers to an angle, yes? So, this is an angle that belongs to some triangle, right? So, okay, I'm going to draw a triangle here. What should I put in it? Well, I've got an angle that I'm interested in. Let's just call it theta for lack of a better name, because, you know, theta, right? And sine inverse of this angle is x on 2. x on 2. So where do x and 2 go on this diagram? Opposite and hypotenuse, right? X on 2. Okay, x on 2. Now, when I do sine of this angle, sine theta, it's no problem because it's just x on 2. Again, that's why I have this. But if I want cos, then what do I have to do? I need this other length down here, right? So Pythagoras, so this is the square root of 4 minus x squared. You can go check it out if you want, okay? Alright, so therefore, cos of this mess is just cos of that angle, which is adjacent on hypotenuse. So the square root of 4 minus x squared all over 2. Okay? Plus my poor lonely constant. Okay, all the actions happening over here is just left behind. Alright, now, after I tidy this up, I'm basically done. Because now everything's, not in terms of thetas, it's back in terms of the variable I was interested in. So this guy is still hanging out the front. These 2's cancel. Cancel, cancel. So you get minus x square root of 4 minus x squared on 2 plus constant. Exhale. Okay, so that was, I told you it was more work, even though it seemed like less work because it was indefinite. You've got to watch out for all of this. Number one, I think the domain restriction's a real catch to be careful for. And number two, you've got to draw a triangle, because otherwise, what on earth do you do with this thing? There's not much you can do. Okay, and they will not accept this as a final answer. But you've got to simplify further. Okay? Maybe one last thing, don't forget your constant, because you're doing all of this stuff over here, and then you'll forget to write plus C.